Hi everyone, I'm Joey Carlson. I'm a PhD student at UC San Diego, studying under Professor Robert Heath, and today I'll be presenting our recent work titled A Wideband Beamforming Algorithm for Dynamic Metasurface Antennas Under Realistic Constraints, which was in ICC 2025. So first, I'll go into a little bit of the motivation and background for this work. So there are a couple of different analog architectures that we could use to do wideband beamforming. First, we could look at a phased array using phase shifters, as we see on the left. And phase shifters usually have sort of frequency flat beamforming, and so for narrower bandwidths, this is maybe okay, but as we go to wider bandwidths, we would start to lose out on some of those frequency selective effects that we couldn't account for. There's also power consumption with phase shifters, lots of components, and insertion loss, and we want to be able to come up with a better solution than this if we were going to do beamforming with large signal bandwidths. Instead of phase shifters, we could also use true time delay components. And these true time delay components allow for wideband beamforming. They have a frequency selective response to them to allow for this, but they are typically power hungry, also have many components, and also have insertion loss. And so while this is an improvement on the wideband beamforming front, there's still additional hardware constraints and limitations for being power hungry and insertion loss that we want to overcome. Now, instead of these two, we could also use reconfigurable antennas to do wideband beamforming, and then specifically dynamic metasurface antennas. So we could use these dynamic metasurface antennas to do wideband beamforming. Each element has a frequency selective response that we can tune to a frequency selective channel, so we can do beamforming in that sense. And there are few components and low power consumption in this architecture to help us overcome some of the hardware footprint and power consumption limitations of phased arrays and true time delays. So then what are dynamic metasurface antennas? These dynamic metasurface antennas are a sort of low power, reconfigurable slotted waveguide antenna array. So we have these slots etched out on a waveguide here with different varactor diodes or other reconfigurable components etched onto the top of them, and we can control these with an external controller. And as we tune these varactor diodes, we can actually enable beamforming. And so the slots will radiate out this energy, we can excite our waveguide, and we can do beamforming with low power consumption, since the varactor diodes are passive components and don't really consume any power. And so this really helps us to do wideband beamforming with minimal hardware, minimal cost, and minimal footprint. Now, of course, having great beamforming and low power consumption, there's going to be some constraints and challenges with the DMA. So first, because it's a waveguide antenna array, there's going to be propagation within the waveguide that we need to account for in the modeling. There will be phases and amplitudes and attenuations that's going to occur that we need to account for in the model to complicate the beamforming approach that we will take. Moreover, because of the varactor diode and how we tune each of the DMA elements, rather than having an antenna weight distribution that is really nice, like an ideal phase shifter, as we see on the right, with 360 degrees in unit amplitude, we instead can characterize the element weights from each of the DMAs by a Lorentzian constraint, as we see in that blue curve there. We see that this is significantly limited compared to the phased array, and so these beamforming limitations for both the waveguide and the Lorentzian constraint can introduce some significant challenges for actually coming up with a wideband beamforming solution. Now, prior work on DMA beamforming has largely focused on using DMAs with small signal bandwidths and assuming a frequency flat response, assuming that Lorentzian constrained weight distribution for a small bandwidth of frequencies in a frequency flat response. Now, shown in the middle there, an example of what the DMA element tuning looks like if you tune that varactor capacitance, so that's C-var in the legend there. Now we see that if we have the amplitude and phases don't actually change very much with frequency. So this frequency flat assumption may be valid for these narrow bandwidths if the bandwidth is very small. However, because of the element response, because of the resonance and the phase and the amplitude, if we have even slightly larger bandwidths, this frequency flat assumption completely starts to fall apart, and we cannot assume a frequency flat response for our different DMA weights. It cannot be ignored. So our proposed work here is to incorporate this frequency selective DMA response and some other realistic constraints for the DMA elements into a wideband beamforming system and propose an algorithm to improve the performance as well. Now we'll get into the DMA model and how we're going to be doing wideband beamforming with DMAs. So for our system model, we're assuming a MISO OFDM system where we have a DMA array of many DMA elements at the transmitter, and we have a single antenna at the receiver. We assume an OFDM system, so we have different subcarriers, and the DMA beamforming, for the DMA elements, our beamforming vector is composed of these different polarizabilities. And so it was shown by David Smith's group over at Duke that the magnetic polarizability of each of the DMA elements, which we can see on the right there, is actually what characterizes the radiated amplitude and phase from all of the elements. And so we have this nice equation here with a couple of terms that dictate the geometry and the design of the DMA, like the damping factor, coupling factor, resonant frequency tuning. And all these things can be incorporated into this polarizability equation to allow for us to have an effective antenna weight to use that not only works at for narrowband cases for frequency flat, but also characterizes the full element response across frequency, which is what we can see there in that DMA element tuning plot. So these will be our effective antenna weights for our DMA precoder across frequency. We see that the resonant frequency tuning there is what is actually tuned by the varactor diode. So if we tune the CVAR value, that will actually tune the resonant frequency, which is also what we see in the plot there. Now, in addition to the system model and the magnetic polarizability, we also want to introduce some other realistic DMA constraints that have not really been mentioned or incorporated in prior work. And so first, when you actually design a physical DMA element and you incorporate a varactor diode into it, there's going to be some limit to where you can tune the upper and lower resonant frequencies. So there's going to be some FR min and some FR max depending on the DMA geometry and the varactor diode that you choose. We incorporate this into our work via a tuning bandwidth factor. So we have both the signal bandwidth and we have the tuning bandwidth, which is the FR max and the FR min that you see there, which will restrict the range of resonant frequencies that we can actually use for our wideband beamforming. Now, secondly, we also incorporate the attenuation of the electromagnetic fields due to the waveguide propagation in our model. So as each of the element radiates and resonates and radiates power, of course that power has to be then subtracted from the waveguide. And so we are using an averaged attenuation model to model this, and we account for this in this waveguide attenuation term here, the G. And then using this, we calculate the wideband spectral efficiency with our DMA precoder that houses all of our magnetic polarizabilities, and this waveguide attenuation to modify that as basically an effective amplitude taper to each of the different DMA element weights. Now, given our model and some of these realistic constraints, we come up with an algorithm here to configure each of the DMA elements based on these constraints. So because of the waveguide attenuation that we just talked about, we know that it applies an effective amplitude taper that is the largest for the element closest to the feed and is the smallest for the elements farthest from the feed. Now that means that elements closer to the feed will transmit more power and have a higher effective antenna weight than the elements further from the feed. And so in order to leverage that, we come up with a successive algorithm to configure each of the DMA elements for wideband beamforming. So we start with maximizing the spectral efficiency and configuring the first element to maximize spectral efficiency. And then given this first configuration, we then configure element 2 to maximize spectral efficiency, and then so on and so forth for each of the different elements until we get to the last element. And so this works not only to leverage the waveguide attenuation and the higher amplitude weights, but it also works to allow for the algorithm to adjust to previous configurations because all the elements further down are affected by that configuration. So it helps to jointly configure all of the elements together based on each other's configurations too, which will help in adapting to the complicated wireless environments in multipath. Now we'll go over a few simulation results using this wideband beamforming algorithm and comparing against a center frequency beamforming algorithm as our baseline. And so the center frequency beamforming algorithm configures each of the resonant frequencies based on the center subcarrier frequency of the channel that we configure. So this is our center frequency and baseline beamforming algorithm to compare against. Now first, on the left, we see the data rate for a specific specific DMA setup. In this case, we have a tuning bandwidth of 500 megahertz, 4 paths, and 12 DMA elements. We find that as the signal bandwidth increases, so does the data rate until we reach a data rate peak and the signal bandwidth starts to decrease. Now, it makes sense that the data rate increases with bandwidth, but it then decreases as the signal bandwidth gets large because it starts to become then the tuning range. So because the signal bandwidth increases beyond 500 megahertz, which is the tuning range, our DMA can't actually handle that. It can't actually steer and radiate out power at those frequencies because of this limitation and constraint on the realistic DMA. And so it seems sort of obvious we shouldn't have a DMA that can only tune to 500 megahertz with a 1000 megahertz signal bandwidth. But because this hasn't been really largely incorporated in prior work, we wanted to highlight it here that it matters a lot for the wideband case. Moreover, we also wanted to see how the DMA did with a different number of channel paths and multipath. And as expected, with multiple paths and more complexity, the spectral efficiency decreases with the number of channel paths, but the DMA successive beamforming algorithm still performs much better than the center frequency beamforming algorithm, showing that it's more it can adapt better to the wireless environment and the frequency selectivity of the channel. Now, in addition to these results, we also wanted to present some design recommendations based on this work. And so first, we vary the tuning bandwidth and look at the data rate for a specific signal bandwidth to see how should we design the tuning bandwidth for a physical DMA in a wideband system. So we find that as the tuning bandwidth increases, so does the data rate, and that makes sense. With a larger tuning bandwidth, we have more resonant frequencies, more weights, more frequency selective weights to play with, which will help us to work with the frequency selective channel and maximize the data rate. However, we find that there is a data rate plateau where the performance does not increase, which is right around 500 or 600 megahertz, matching with the signal bandwidth. So this is an interesting insight that if we have a wireless system with a 500 megahertz signal bandwidth, with a certain signal bandwidth, we do not necessarily need to design a DMA with a 10 times more of a tuning bandwidth. We can design our DMA to have just about the same tuning bandwidth as the signal bandwidth, and we'll just about maximize our data rate. And moreover, we also wanted to look at how varying the quality factor, so the amount of the sharpness of the resonance, and how that affected the data rate results. We found here that over different quality factor values, the data rate does vary a little bit, but it largely stays somewhat even for our DMA successive case, though there is a certain range of optimal quality factor values that does maximize the data rate there. And that is mostly due to, I think, having a very sharp curve increases the flexibility, but also having a very broad curve will lead to lower amount of antenna weights. And so there is sort of a sweet spot for the quality factor that you'll want to design your DMA for a wideband system with a certain bandwidth. So now we'll talk about a few key takeaways and future work. So in this work, we designed an improved wideband beamforming algorithm for our DMA system. We incorporated a realistic wireless channel model and wireless system model that is frequency selective and has multipath, and incorporated other realistic DMA constraints into the model, like the tuning bandwidth and the attenuation. We then developed a wideband beamforming algorithm that outperformed a center frequency beamforming algorithm by being more adaptive to the wireless environment, the frequency selectivity, and the other elements for the DMA that we already had configured. So then, in future work, well, in this work we focused on just doing beamforming for a single DMA. In our planned work, we hope to extend this to what we're calling the tri-hybrid architecture, where we not only have a single DMA, but we also have digital and analog signal processing thrown into the mix to help overcome some of the limits of the DMA, like the Lorentzian constraint and the waveguide effects with the phase advance and the attenuation. And so this will allow for a joint digital, analog, and DMA signal processing, so further complicating the signal processing, but for hopefully we will see improved benefits with the whole tri-hybrid system. Thank you for listening, and please refer to the full paper for additional details. Thank you.